Welcome to Chapter 18 on electric charge and the electric field. Um, Electric charge and static electricity and charge something goes back all the way to Benjamin Franklin, and you will remember stories of him flying a kite in a thunderstorm. Not exactly true, but he did do some fundamental work on electricity. In fact, the electrical engineering department at Cornell, their building is named after Benjamin Franklin. His contributions were fundamental, so fundamental. One of the things he did, though, that he got wrong is he had to guess about which way electricity actually flows, and he had a 50-50 chance of getting it right, and he guessed that it flows from positive to negative. But it turns out, now that we have been doing this for a while, we know that electrons are the primary carrier of charge and electricity, and they flow from negative to positive. So, um, what is the fundamental charge? All right, this is a very bad illustration of an atom, but we'll go with it. Um, so the nucleus, the protons are positively charged. The electrons are negatively charged. This is simply a sign convention. You could reverse that convention everywhere and all the math would still be the same. All works out just beautifully. But charge on the electron is minus 1.6 times 10 to the minus 19th coulombs. And the charge on the proton plus 1.6 times 10 to the minus 19th coulombs, named after Coulomb, who did a lot of the fundamental work on electric charge. Charge is conserved. If we have a neutral charged object and a neutral charged object, and we somehow get them to exchange some charge, what we get away with, what we get in the end, is there might be some net charge on one of them. All right, like this one has a net minus 2, this one has a net plus 2. But if you look at the whole, the net is still 0. Charge remains conserved. We group materials into conductors and insulators. And there are a few other groups like semiconductors and superconductors, but primarily conductors and insulators. A conductor allows for the free movement of electrons. Now, not completely free. A superconductor, it's completely free. And by completely free, I mean there's no energy loss. In a conductor, charges move readily, but there's some energy loss as they move, mostly due to collisions. And you can show this by taking a metal rod, take this charged metal rod, put it near this device, which has an isolated little metal foil down here. These positive charges attract negative charges, makes this down here net positive. Because this is the net positive down here, the little pieces of foil repel each other and spread apart from their starting position. And you can actually leave a net charge on this by touching them together. We may or may not be able to do this experiment depending on how dry the air is in lab next week when we get to this. So there's charge by induction, right? So you've got these two spheres touching each other. You bring a charge rod near them. Charges separate on the two spheres, and you take the two spheres apart. Now you've got a voltage, well, you've got charges, a net charge on this, a net charge on that. But again, this started out with 0. This total is still at 0. Charge is conserved. In an insulator, charges do not readily move. In fact, charges are more tightly bound. In a conductor, charges are very loosely bound, if bound at all, to the atoms. So in an insulator, they do not move much at all. And insulators, typically you can polarize, i.e. we can get a little excess positive charge here and a little excess negative charge there, but you can't get charges to actually start moving around. And the reason is you've got all these little bitty atoms, and all you're doing is you're reorienting the atom. You're not actually getting charge to flow anywhere. And it's that net orientation of the atoms in the material that gives rise to a net positive and a net negative, but no charge has really flowed from one side to the other. Whereas if this were a metal, like in the previous side, charges moved around. All right, charges moved around. Here, we simply rotated atoms around to change um, the overall charge distribution by just a little bit. Coulomb's law is the starting point for how forces on charges